Alright, so let's do FRQ number 2. So, number 2, part A, wants us to find the speed of the particle at 2. So, here we have a graph of force versus distance. So, in order to find the speed at 2, we first need to set up force to find acceleration. So, at 2, we have force is equal to -5. So, -5 is ma, -5, and our mass is 4 kilograms. So 4 A equals -1.25 meters per second squared. Okay. So now what we can do is common form. Okay, so let's start plugging in what we know. We know delta x is 2. We are finding VF, and it tells us that it starts at 6 meters per second. So that means our VI is 6, and then 2, and we just found A. Okay. So now we'll go ahead and solve for VF. So VF is about 5.57 meters per second. Okay. Now, this makes sense as well. We can kind of check to see that we did it correctly. Because our force is negative, so that means the force is acting against us. So that means it is going to be slow. The particle is going to be slowing down. So that makes sense for the situation. On to part B. Find the time of travel from 0 to 2. Okay. So we can go ahead and set up this. And we're just going to use what we found and what was already given to us. So we know that speed at 2 is 5.75. We know our VI is 6. We found that A to be -1.25 and T. Let's go ahead and isolate for time by bringing over the 6. And that is our time. Okay, on to part C. it wants us to find the impulse experienced by the particle between 2 and 4. Okay. So, first let's set up torque, or not torque, sorry, impulse. Impulse equals MOV, as I like to think of it. So, let's expand this a little. So, VF, so delta V always means VF minus VI. So that is what we are going to use. But the problem is we do not have the speed at 4. And as you can see here, we can't do our normal force, F equals ma, because there's this slope here, and that makes it a little more tricky to find acceleration using this. But what we are going to use is the work kinetic energy theorem. So, as you can see, our graph, again, is force versus distance. So, we know that work equals force times displacement. And then we also know the kinetic energy theorem. So we're going to use this to find our VF. So what we're going to go ahead and do is find the energy, find the work, from 2 to 4. And that, so we want to find it from 2 to 4. And that is because you have to remember it is delta x. So, and then we also, if you want to use this theorem, you have to remember that it's sigma work equal to change in KE, and change in KE means it's going to be VF minus VI. So we need to account for that for this whole distance. So let's go ahead and do that. And the way we're going to do that is you find the area of the graph. So from here to here is 1 times -5 is -5. And then area of a triangle, base times height over 2. So 1, and then -5, so -5 divided by 2, -2.5. And since these are both below the x-axis, we can just add them. So sigma work equals 7 or -7.5 joules. Now with that, we can set it equal to KE, but we want to expand it because remember we're using change in KE, but we're going to expand it. So 1/2 mVf squared minus 1/2 mVi squared. Alright, so now we just plug in everything that we know. The mass is 4. We are looking for the VF. Okay, now VI. So it wants the impulse from 2 to 4. Now remember, we already found the speed at 2. So we can just plug that in. So and just go ahead and solve. Okay. So now with that, just want to isolate for VF. So go ahead. Okay, so we have found speed at 4, and in this case it's gonna be our VF. So now we can just use this to plug it into here. And if you remember, so it's from 2 to 4, so our VI is going to be speed at 2, which we already found. Joules. Okay, so that is part C. On to part D. Okay, so again, impulse, but not wants it. Go ahead and erase. And erase this. Start from clean. So it wants it from 3 to 5. Okay. So we're gonna have, this is gonna have quite a few steps to it, but let's go ahead and set it up. So we're gonna use impulse equals mauve again. So the thing is, we do not have speed at 3, nor do we have it at 5. So we have to go and find them. Okay, so first we want to find, let's start with 3. So for 3, we can use this because, as you can see, 3, there's a constant force. So we can still use our whole finding acceleration and using common form. So we can just set up common form because we have already found acceleration. So delta x is going to be 3. We are looking for VF, and again, VI is 6 because it tells us. And we're just using the A that we had already previously found. And technically this is our VI, so I'm just gonna write VI in parentheses just because for the problem it wants us to find impulse from 3 to 5, and so this is the speed at 3, meaning that is going to be our VI. So now we need to find the speed at 5. So what we want to do is set up the whole work kinetic energy theorem again. So using our graph again and finding the area, we are going to find the kinetic or the work for this section right here. So again, remember base time height over 2 to find the area of a triangle. So 1 times 5 over 2 is 2.5. And now it is positive because it is above the x-axis. So we can set up a change in KE. It's just equal to, okay, so 2.5 is equal to 1/2 mvf squared minus 1/2 mei squared. Okay, so if you noticed, I did it from 4 to 5, so that, and we have already found the speed, we have already found the speed at 4, so we can go ahead and just plug in that for our VI. So we found it to be 2. Okay, so now we just simplify. Okay, so now we just want to isolate for VF, bring that over. And if you're noticing, we are going to get the same speed for both. So what that means is there is no impulse, because what's going to happen is we're going to plug in the speeds that we found, and we're just going to get 0. So that is part D. Grab a new piece of paper. Okay, so on to part E. Okay, so it wants us to find the speed at 10. Okay, so if we look at our graph, we can see that this line keeps going, and that 10 is going to be about here. So that means we can go back to our force to find A, and then from there we can use common form once again to find VF. So let's go ahead and set that all up. But now we're positive. We're at 5, not -5. So that is our A. Let's go ahead and set up common form. Okay, so now we need to pick a spot to start from. So I'm going to start from 5 because that is when the line starts to plateau, and that makes it easy because that means the force is constant, and that means I can use the A that I found. So I'm starting at 5. So from 5 to 10, that's a delta x of 5. We are looking for VF. Now our VI, we have already found the speed at 5. So we're just going to plug that in. Then our A that we just found, go ahead and plug that in the calculator. I want to solve for VF. Okay, so speed at 10 is 6.4 meters per second. And now I'm going to explain this a little bit. Just so earlier we were getting smaller speeds. Earlier we were getting smaller speeds, and that was because our force was negative, so that means it was acting against us. Now our force is positive, so it means it is acting with us, and that means it's going to actually accelerate us and not slow us down. So 6.4 is an increase from its original speed, and it's also an increase from previous speeds, so that checks out. Okay, so part F. Part F, does the particle turn around at some point and head back towards the origin? So let's look at our graph. Erase it. Okay, so we see that it is decelerating all the way up until 4 meters, correct? Now, we found the speed at 4 meters. We found it to be 5.22, and that is not negative. So that means it never turns around. We have found the speeds to all be positive even when the force is negative. So that means that the particle never turns around. So no, particle never turns around because we have already found the speeds, especially focusing on when the force is negative. When the force is negative, all the speeds are positive, which indicates that this particle never goes left. It continues going right. So that means the particle never turns around. So, part G. It wants us to repeat F. So does the particle turn around? But this time, our VI is 2. Okay. So, last time we were looking at till 4 because that's when our force is negative. We want to do that again, but now with our new VI. So, let's go ahead and we can do and so we're going to be looking at the work from 0 to 4. So that means this area plus this area. 3 times 5, 15. And then base times height over 2. So 5, negative 5 over 2, negative 2.5. And we can go ahead and add these because they are both under the x-axis. So that means negative 17.5 equals 1/2 mvf squared minus 1/2 mri squared. Now, what we're doing is we want to find vf at 4, because we know that after that the speed is just going to be accelerating. So we want to see what the we want to find v minimum. So that's what we're trying to find, because if v minimum is negative, that would indicate that the particle does turn around. So we need to figure out if v minimum is negative. So let's go ahead and plug in everything. And we're using our new VI that it gave us. So 4 times 2, right? 2 squared 4, it's 2, so 8. Okay. Okay, so what we have found is that at this 4, the speed is negative, which indicates that the particle has turned around. Because remember, when velocity is positive, that means it is going right. When it is negative, that means it is going left. So it started at 2 meters per second, positive, going right, but now here, when we are at the 4 meters, it is going left. So that tells us that the particle has indeed turned around. And that concludes FRQ 2.